So hi everyone, welcome back to another Stark at Home. My usual first question is, can you hear me? So please, can someone type in the chat room? Can you hear me? Just checking that the mic works. Okay, thanks Johan, thanks Chloe. Okay, so super excited to have another Stark at Home episode, and this time we're going to do a deep dive into the Cairo white paper. So you'll hear a lot about Cairo in a minute, and you'll hear about it from the three co-inventors of Cairo and also co-authors of the Cairo white paper. They are Michael Ryabtsev, co-founder and chief architect, Ariel Goldberg, who's Lior Goldberg, who's right. Sorry, I'm as I said, I'm very excited for this episode. So Lior Goldberg, who leads the StarkNet engineering, and Shachar Papini, senior engineer at Starker. All of them are the co-inventors of the Cairo white paper and the Cairo framework, which we're very excited about. Also with us, we have to sort of query and ask and give another viewpoint on writing, Turing complete frameworks for blockchains and ZKPs. We have Alexei Akunov, who's an Ethereum developer, or could be referred to as a core Ethereum developer, and also he leads the Aragon project. And we also have Kobi Gulkan, who does applied cryptography at C Labs and is a Snark Wrangler at large. So the plan is we'll have briefly a 10-minute introduction to Cairo and what the white paper does. Then we'll have a brief stop for questions, another 10 minutes by the Cairo co-authors about high-level description of things like built-ins and the public memory, which is important for using Cairo and StarkNet. And then we will hand it over after 20 minutes or so to the esteemed guests. And you'll notice that there's the Ask a Question button where you can ask, so here's a test question, and then we can answer it, because it's much easier to use that thing rather than the chat room. Okay, so I'll hand it over to the Cairo co-authors. All yours.
I'll start with a quick intro. I'm Michael. I'll start with a quick intro to what can you find in the Cairo paper, and later Lior will dive into the unique memory model in Cairo, and Shachar into the built-ins. Eli, can you please help me and give me a whiteboard?
Mm-hmm. Oh, wait. No, wait. So we are going to share a screen. The screen is good. There we go. Okay, let me just check that it is shared.
I think it is.
Yeah, now it is.
Okay. Okay. So I did something bad.
Wait.
Everyone.
I'll do it with the pad.
I think
here it is. Okay. Can you hear my cursor? I guess you can. So yes. Okay.
We can see the cursor.
Great. So if you heard about Cairo before, what you usually have seen is the.
You could try it. It should work.
It doesn't.
Okay, so we have some technical difficulties.
Okay.
Do you want to use mine?
I'll go and try to use yours.
Yeah, so sorry about it. Can you stop sharing?
Yes, I'm going to share the whole screen. So, and those who are not familiar should know that Stark at Home is a very informal setting, as you see right now. So I'm going to share the whole.
No, I'm going to share. Oh. I don't know. Okay.
Now you should share your screen.
Okay.
Okay.
So can you see my screen?
Yes, and I'm going to
Okay,
make
and now I can even write.
Okay. Let me check. One second. So.
Yes, it works.
Okay. Great.
Okay, so sorry about the technical delay. So you probably heard and seen the Cairo language. And you know that somewhere in the end, it is provable with Starks. But what happens in the middle, and the paper focuses on, is that there is a Cairo bytecode. That the Cairo language is compiled to. There is a Cairo VM, a virtual machine, which can execute the Cairo bytecode. And there is an error, which is a set of polynomials used as constraints, used to prove executions of the Cairo VM. So what we will, what you can find in the paper is mostly focused on this, on how exactly the Cairo bytecode looks like, how can it be executed with the virtual machine, and how is the error to prove the virtual machine looks like. And we dive a lot there and describe the design choices that we did, when most of them focus on how to make this part as efficient as possible. So if the only thing that you want to do is to write Cairo code and make it work, you don't really need to read the paper. But if you really want to understand how it works and why we chose such a language, then this paper can really help you to understand. And now I'm moving on to Lior, who will explain our unique memory model.
Yes. So as Michael said, when we thought about the design of the language, of the intermediate of the instruction set of Cairo and so on, the focus was making the error as efficient as possible, while still letting the users write meaningful and meaningful programs. Okay, so I want to clear frame, great. Okay, so one thing, if you want a Turing complete language, you should have some kind of memory. A finite set of registers, for example, is not enough. And if you need some kind of memory, you need to choose a memory model. And there is an obvious choice. The memory model that we are used to from the x86 architecture, basically a read-write random access memory. And we didn't choose this model in Cairo, and I want to explain why and to describe what memory model we did choose. Okay, so the question, as we said, is how efficient it is to build the error, and memory is challenging, and the reason that memory is more challenging than other types of instruction and handling registers and so on is that the requirement for memory is a global requirement, and the polynomials that we can put in an error are basically local. So the way it's solved is that we take a list of memory accesses that happened in the program. So we have the time, when the operation happened. So we order the list chronologically, so the time increases. We have the operation. The operation can be either read value or write. And for each memory access, we also have the address being accessed and the value. If it's a read operation, then we write here the value that was read from the memory, and if it's a write operation, we write here the value that we are going to write. So for example, address 0, I read the value, it's 5. And now the question is, how can I check that this table is a valid memory? For example, let's say that I have that here I write the value 7 at address 1, and here, let's say these are different addresses, and I'm reading the value of address 1, and it's 8 here. So this is not consistent with this. And if I wrote the value 7, it should be, and I'm reading it, and I didn't change it between, then I expect to see here 7 and not 8. And this, as I mentioned before, this is a global requirement. It's very difficult to check this in a straightforward way in an error. And what we do in order to solve this is we sort the list first by the address and then by the time. So we take another copy of the list that is simply sorted in a different way. And you can see that after such a sorting, this row and this row will be next to each other. So I'll have it somewhere here, address 1, time, I think it's 1 and 4. It's a write and read operation, and the values are 7 and 8. And now I only need to check consecutive rows, and I can say if the list is valid or not. Okay, so basically, these are the things. If we wanted to take the read-write approach, these are the things that we would have implemented in the error. And there are a few things that makes this complicated. One, we need to check the sorting, not the sorting, that the second list is a permutation of the first list. Apparently, so this is actually something that's rather easy to do in an error. You want to say something?
Interaction.
Using a phase of interaction between another phase of interaction between the prover and the verifier. I won't go into this. The second thing is that we need to handle this read and write thing, and we need to check the sorting. We need to check that the address increases and that the time increases inside each segment of addresses. So if I have the same address, I need the time to increase in this direction. So apparently, the fact to check the sorting of the addresses, it's not too complicated because we can add a restriction that the address space is continuous, and then in order to check that it's sorted, I only need to check that in each, when I move to the next row, it's either the same address or the address is increased by 1. So this is also solvable, and the main problem and the most expensive thing is checking that the time is sorted within a section, because when you write polynomial, okay, so checking that a certain value is larger than another value is not something that's natural when you are dealing with finite fields. And it's possible, but it costs relatively to the other things, it costs a lot. So read-write memory is relatively expensive, and we are doing, actually in Cairo, we are doing four memory accesses in each instructions. So it's very important to have this part as cheap as possible, and also memories used in other components, as Shachar will describe in a few minutes. So it's very important to have this as efficient as possible. And for this, we came up with the idea of using a read-only memory instead of a read-write memory. So a read-only memory is much cheaper because first, you don't need this. Everything is read. It's read-only. And you don't care about the time because if it's read-only, it doesn't matter when you accessed it. All you need to check is that if you have the same address, then you have the same value. So you don't need to deal with the time. And in particular, you don't need to deal with the sorting of the time. So moving to a read-only memory simplifies everything by a lot. The only problem is that you can't really write any meaningful program with read-only memory. You can't write to the read-only memory. And here we take advantage of the fact that Cairo runs in a non-deterministic environment. The prover that wants to convince the verifier that some claim is true knows in advance everything, and it can initialize the read-only memory so that everything will be fine. So it's not really a read-only memory. It's more similar to a write-once memory because if, for example, if I want to write a value, it's true that technically I won't be able to write, but it's enough to just have an assertion that the value, for example, in address 0 is 5. This is enough. This is equivalent to a write-once operation, and it turns out that with this kind of memory model, which is more similar to a write-once memory model, you can do basically most of the things that you need, and if you need to do things that you can only do with read-write memory, then you can simulate full read-write memory on top of this non-deterministic read-only memory model. Okay, so this is the memory model that we chose. If you have programmed with Cairo, then you probably saw that everything is immutable, and now you know the reason. Okay, so now I want to describe an advantage of this memory model, which is the public memory. So let's take an example from the blockchain world. In many applications, you need data availability, on-chain data. You need to have a program needs to put some data on-chain, just so the data will be available for anyone that has access to the chain. The contracts, that the L1 contracts doesn't need to do anything with the information. They just need to verify that it's there. And usually it's a lot of data, so it's important that it will be very, very cheap. And if you go with this read-only memory model, it turns out that all you need to do in order to share this information between the prover and the L1 verifier is just to add to this list at the end, and this can be done virtually. You don't actually need to allocate memories, to allocate traces for this. You just need to add here a set of addresses and have, so let's say A plus 0, A plus 1, and the set of values. You just add it to the list, sort it with in the same way, and it just works. Since the memory is read-only, you don't need to care about overriding values and so on. So it's very simple, and the cost is only, so you need to pay for the hash of the data, and you need to pay for like something like 4 arithmetic operations in the field, which is very, very cheap, 4 arithmetic operations per such entry. So this is much better than what we thought as the. So let me describe the naive solution maybe. for this problem. The native solution is you put the data on chain and you compute the hash of the data, both in the program and in the L1 contract, and you compare the hashes. And this sounds good, but for this to work, you need a hash function that is both cheap on L1 and in the proof, and apparently such a hash function is, okay, we are not aware of such a hash function. So in this approach, you only need the hash function that's friendly to L1 and for arithmetic operations.
How much gas does it cost?
How much gas does it cost? So I think it's around so 700 gas per 32 bytes per Ethereum word, and this is this is very cheap. Most of this is, by the way, only the transmission of the data to the chain. Okay, so now Shachar, do you want to describe
There's a question.
Yeah, question.
There's a question here, and I remind the audience again that if you have more questions, I'll read the question and someone answer. Can you expound on why you need to execute the bytecode in the Cairo virtual machine? Is it to create the auxiliary inputs that are needed to correctly verify the execution trace in the air?
So I'll take this.
Mm-hmm.
The reason that we don't prove directly the Cairo code, but we have a virtual machine, is to have this virtual machine is a universal machine that can execute any algorithm written in Cairo. This allows us to write a single constraint system of polynomials that you can use universally to prove any program written in Cairo. So this way we can deploy a single verifier, for example, to Ethereum that verifies the statement of the Cairo virtual machine executed a program with, for example, this hash of the program, and this was the output or something like that. And you can have this single statement, and it can be used for any Cairo program. This is why we have this another layer of abstraction.
I just want to make sure that the question was indeed on the Cairo VM, not the Cairo runner. Sometimes confuse them. Just to say why we have a Cairo runner, it's indeed to create the auxiliary input that we give to the prover. Yes, we have this Python that runs it memory. It doesn't have anything to do with proof. It takes everything and gives the witness to the prover.
There's another question. What was the rationale behind explicitly exposing the user to the read-only memory model versus making it seem like you have a read-write memory model and doing the transformation in the background?
Well, I think it's mostly efficiency and the fact that it really doesn't bother writing anything in the language. Okay.
Yeah, so you definitely can write a programming language that will compile to the Cairo instruction set and will hide the fact that the memory is read-only, and everything will be with this read-write simulation, which, by the way, you can read about in the paper. But yeah, it's less efficient. You want it's very
And not only less efficient, it's also more safe. We get a lot of safe benefits from having an immutable memory. A lot of things that have in regular computer that somebody writes on this value and changes it somewhere, they don't exist.
Yeah, and by the way, functional languages has
a thing.
Has the same feature and without technical requirements. And they also so working with immutable memory has its own advantages.
So you are just commenting in the chat. I guess it does mean that you can't have loops that cannot be unrolled. But please put questions in the questions.
So you can have loops. So first you can have recursion.
That's what functional languages do.
Yeah, again, so you can have recursion. So it's Turing complete. You can do whatever you want without needing. You don't need to specify bounds or anything like that. You can actually have loops in Cairo as long as you plan them correctly. As long as you don't need to rewrite on cells that you've used and you just progress with the cells and every iteration write on new cells, you can definitely write loops.
You can look at the memcpy implementation, standard library.
Yeah, which uses a loop.
Maybe you want to put it in the chat while he.
Yeah. Okay, I'll do it.
Okay.
Okay. I don't have a lot of time, so I'll try to be brief. I just want to talk about built-ins. Like we just said, Cairo is Turing complete. You can do anything you want there. You can even make you coffee, but sometimes it's not very, won't be very efficient. So we knew from the beginning we wanted to have to be able to incorporate raw error components, for example, hashes that are not written on top of Cairo, but are written beside Cairo on plain errors. So it'll be very efficient. The question is, how do we incorporate and communicate with the program? Well, the naive approach would maybe be adding a specific opcode for this hash and maybe repeat every a couple of steps, so it won't be very much. The problem with this is everything you don't use, it goes to waste. You can't force a program to have hash every 8 steps, or something like that. You want the usage to be dynamic, so you only pay for what you use. Unfortunately, there are ways to do that. The way we chose is using the memory. Basically, we have our main CPU component that has memory units, like we just talked about, and alongside it, we have, for example, the hash built-in, which is a hash written error, along with its own memory units. So the CPU has memory units, and the built-in has memory units, and at the end we combine them and with the constraint to say they come from the same memory. And together with the fact that the memory is read-only, where the CPU can know that if it reads from this address that it belongs to the built-in, then it is enforced by the built-in.
Do you want to draw it? Or?
No, I did not want to draw it. I wanted to be brief, and I was brief. So if you have a question, you can say. I just want to say that the built-ins are independent of the CPU. It's not that Cairo comes with CPU and hash. We can play with it and put more built-ins, less built-ins, more kinds, a lot of specific kinds. It's pretty independent.
Yeah, the fact that the built-ins are not part of the CPU and they talk to the CPU through the memory gives us full flexibility in adding new built-ins or removing existing built-ins. And it gives you the control of how many instances of the built-ins you want to put in a proof, which gives efficiency again.
So there are 2 questions. The first is, what about, Marcos is asking, what about support for dynamic list?
Yeah, so you have full access to the memory, and you can create
everything with a value and the pointer to itself.
Yeah, you can definitely create it. It's maybe more a question to the higher level language, how it is supported and so on, but also in the higher level implementation of Cairo, you can easily create.
I wonder if there are examples also in the code, like the case of loops. Is there an example of a dynamic list somewhere in our code?
So it depends on what dynamic list means. If it's a linked list, we have it in the Cairo games. There is a linked list somewhere. You can take a look at the Cairo games if you haven't. Then
if you want something like we have an appendable array, which is just a pointer, more or less.
Yeah, it's also described in the paper, and you can find it in the code.
Yeah, something neat maybe to mention from the paper, because Shachar mentioned the appendable array. You can read about it in the paper, but in contrast to classical languages, when you need to manage memory and, for example, need to allocate memory for an array, and if the array gets bigger, I need to somehow reallocate memory and manage it. In Cairo, it becomes trivial. I won't go into it now, but just look in the paper, it's very elegant.
Because non-determinism.
Okay, so another question. Do built-ins have proofs? If so, how does that work? So Bengt is asking.
So I'll try to answer, but I'm not sure that I understand the question. Built-ins are part of the air, and the fact that so they are proven with the air in exactly the same way. It's not a separate proof or something like that.
You can think about it, it's like in additional columns in the same air. You can think about it like this.
Yeah.
Okay, so yes.
So the answer is yes.
They are part of
if I understood the question, yes.
Okay, so now I think we're turning it over to Alexei and
Kobe.
wait a second, to Alexei and Kobe. Yeah.
Okay. Hi everybody. Alexei. So I've prepared a couple of questions, and some of them are about built-ins. But first of all, what was your motivation to create Cairo in the first place? What was there must have been specific challenge that you faced, and then you decided, okay, now we've got to create something like Cairo. What was that actually pushed you to create it?
Okay, yes, this is a good question. So when we started, we built our first big project was building an exchange, and we wrote the polynomial equations basically by hand, and we did it, and it was this air was in production for I think 6 months or so. But after we did it, we understood that this is a difficult thing to do. If you need to write everything as equations, and even things like checking that a certain number is more than another number, which is something that you need if you want to check that orders matches. Even the simplest things are difficult to do, then it's very complicated to build a very sophisticated system, and you can't use trivial algorithms, because just implementing the algorithm is too complicated. I think this was at least my main motivation of building Cairo. If you have one set of equations that can do basically everything, then all you need to do is just write code. And code is apparently, it turns out that code is more efficient in some aspects. So it's true that every instruction of the code is more expensive, but once you're given the ability to code instead of writing equations, you can do more sophisticated algorithms and improve things this way, and you don't need to deal with the limitations of writing an error. So I'll give just one of them. So in R, everything must be periodic in a period which is a power of 2. This is very annoying when you're trying to do things. So yeah, in code you don't have this problem. Do you want to add?
I share the same view.
So you're essentially, what you're saying is that it's kind of the traditional, like where you're trading the time of the computer for the time of people, right? And you say the time of people is more expensive.
Yeah, I mean, at the beginning, we before we did it, we thought like, okay, we are really willing to live like X5 or something because it's worth it. Practically, when we deployed it and applied the optimization, it was more efficient than the previous version because we had because of the built-in and the fact we had like optimizations on our Merkle to be built. Yeah.
Okay, thank you. Yeah, so I think I will hand over to Kobe now for his question.
Okay, sounds good. So I guess what I thought may be useful for everyone here is to maybe do a small recap. So maybe it would be nice to see what is, very, very briefly, the difference between, air and other representations, and why a CPU approach works nicely in air. And maybe in the same vein is what is the dependency of verification on the trace cells and how it all plays together.
I didn't just hear the very last part. What is the effect of?
The dependency of problem verification time on the amount of, let's say, the trace cells.
The proving time and the verification time, the dependency on the number of traces.
Okay.
Things like that. That was the first question.
I thought it was air. Why is air? Okay. Yeah.
So let's start by, you can answer the second question and then we go back to the first.
Let's see if I remember correctly. I think the proving time is like a n log n, something like this, because there are FFTs in the trace cells. No, it's not really the number of trace cells, because you have a trade-off between the number of columns and the rows, which you trade off with the verified time, but it's more or less n log n. The verification time is like log squared or something, right?
Yeah, something like that. In practice, so the effect of Cairo here that doesn't play a role. So it's the numbers are very similar to, and the asymptotics are very similar to Stark in general. So yes, it's n log n, but in practice it's basically linear. The log n doesn't change by a lot, and the verification time is theoretically log squared, but in practice it's constant. So the overhead is so large that you almost don't feel the log square there. Mm-hmm. And the first question, Kobe, can you repeat it?
Yeah. So just a small recap of the difference between air and other representations, and why CPU approach plays nicely with air.
Okay, so the question is, okay, so basically the problem with, so as I mentioned, the problem with building an air is that you need to do everything with periodically and
local constraints.
And the constraints have to be local. And if you want to do, for example, an if, this is an example from again, StarkX, there are a few types of transactions. You can have an exchange transaction, and you can have a transfer. An exchange is two orders with two tokens that matches, and you swap them. And transfer is just one user transfers funds to another one. So transfer is cheaper. So it should cost about 1/2 of an exchange. But when we did the air, since everything need to be so
you had the space for one transaction. You need to allocate it by the largest transaction.
Yeah, so you paid for a transfer the same amount that you paid for an exchange without any justification, and you had to not use the cells so half of the cells. So this is an example where in code you simply write an if, and if this branch is happening, then you're only doing this branch, and if not, then you're going to the other branch and do that. So this is one example where you really want to write code and not equations.
Yeah, I just want to mention that it seems it fits doing CPU in air because most of the constraints are just local, between this state and the next state, along with memory. So you need the trick with memory, but other than that, it's like local constraints.
Yeah, so memory is the only global thing, and as we discussed earlier, it can be solved, and it turns out it can be solved actually very efficiently. So we have only five trace cells per memory access, and if there are snark guys here, so it's equivalent to 5 multiplication gates in snarks. This is very, very cheap. And the other constraints, as Shahar mentioned, are naturally local.
Mm-hmm. Kobe, maybe I misunderstood the question, because I thought that maybe you asked how can airs be compared to other common constraint systems from proof systems, or this was not what you meant?
I think like the answer was good, because what I wanted to get is exactly why, CPU works nicely with R. And I think the answer was, if I recap it very shortly, is that, it's much easier to do local constraints when you're working with a CPU approach and you're working with some opcodes that change one state to another. And then it makes the trade-offs between designing opcodes rather than designing very high-level operations of transfer and exchange much easier to play with the trade-offs that you have and how it affects proving them and so on. So I think that was a good answer. Thanks.
I want to say that there are 3 questions. So the question, I guess, to Alexei and Kobe, do you want to ask a few more and then we'll attend to those questions, or should we deal with them now from the audience?
I mean, it's up to you. I mean, okay.
I decentralized this.
All right. Okay. I don't know. I say okay. Let's do one more round of questions from me and Kobe, and then we turn into.
Terrific. And then to the audience, we're
yeah. So
add more questions and we'll attend to them. Okay, shortly. Yeah.
No question will be left unanswered. Yeah.
I wouldn't
right.
Okay.
So basically, once I read the Cairo paper, which I did read actually. So and I invite other people to not take my word for it, but just check themselves. So one realization I had that when you first look at Cairo, you see the examples. You see this kind of Pythonic syntax. You think, oh, this looks like Python with some extra stuff, and I don't understand it. That was kind of my reaction. It's like, what is this? And then when you read the Cairo paper, you realize that the actual the Cairo's got this very, I would say, minimal like a bytecode, which has got some opcodes. I don't know how many, because they're it's not it doesn't actually give you the list of bytecodes, but it gives you the format of how the bytecodes can be constructed. And another interesting thing you notice when you read the paper is that the whole semantics of the machine, if you call it this CPU as a machine, can fit into essentially like a little bit less than 2 pages of pseudocode. You can look at I think it's page 33 and 34, and actually, which is actually that kind of reveals to you that no, you don't really have to. If you really hate the Pythonic syntax, you may actually generate the bytecode, for example, if you understand the semantics. So I'm curious about what is the feedback you received so far on the language itself that you proposed, and do you think that a lot of people will be generating bytecode or handwriting the bytecode instead of using Pythonic language?
Well, you can start by describing the feedback you got from me, and then
so I think this is an interesting question. We didn't get any feedback that says, well, I can't use it. We got a lot of feedback about the syntax. So most of the feedback was that using hints is something that's complicated. We didn't touch hints in this, but hints is the way we describe the non-deterministic part, which Cairo lets you do. So we got this is the main thing that people said, but this is something that if you want. So it's not directly about the syntax of Cairo. I think that people would rather have a syntax that's more like Solidity, because this is what they are used to.
That's not my feedback, but okay.
Yeah, but okay, yeah, you will tell your feedback in a second. I think these are the main things that we had.
Yeah, I just want to say that we indeed, internally, when we started working with Cairo, we worked in the assembly level. Like everything was written in the assembly. And, as we worked, we needed some extra features, some high level syntax sugar things. So it just evolved on its own, adding this feature, and this feature. And that's why today in Cairo you can also write assembly and it just works. It's a combination of all these things. So one thing I want to say that we do plan to add some high level features, so you can use Cairo in a more safe manner that looks maybe a bit better to program. And there are some projects that we have ongoing about compiling from other languages, like the Warp team that they are compiling from Solidity, or actually from Yule to Cairo. And there's another project that works on compiling from Idris, which is like Haskell. And we are also always open for suggestions on the syntax and other things.
Shall we now answer some questions from the
I think
audience?
we will finish the round with questions from Kobe.
Okay.
Okay, I'll ask another one then. So maybe I'll jump to this one. So one thing that I found very interesting when I was reading the paper is that, if people read about Starks a few years ago when things just started, maybe they started from the Vitalik post, and, the version that's described in the Cairo paper, it uses wraps, right? And that's like an upgraded version of Stark that can support permutation argument using an interaction step. So I think you touched on that like very briefly in the beginning, but maybe you can motivate that a bit, and how does that work essentially?
So to motivate what?
Why we use wrap instead of
plain
errors?
Yeah, how it helps, to build these permutation arguments and so on.
Okay, so first, so I'll start by saying that you can read it in the paper, and I will try to give the high level, but I won't be able to go into all the details. Yes, you need interaction in order to convert this global problem of memory to a local problem. Specifically, you need the interaction to check that two lists are permutation of one of the other. And the way it's done is basically that you take, if you have a list of values, you can translate it to the zeros of a polynomial by taking x minus the value and x minus each of the values and multiply all of these, and you get a polynomial that the zeros of the polynomials are the values of the list with multiplicities. And if you do the same thing to both lists, you get two polynomials, and if the lists are permutations of one is a permutation of the other, then you get the same polynomial, and this is if and only if. And once you have two polynomials, you can just substitute a random value, and here comes the randomness, a random value, and compare the two evaluations. And a nice thing about using polynomials of relatively small degree in a very large field is that you need one sample in order to check whether the two polynomials are the same or not. So this was a bit more mathy, but I hope this answers the question. This is where the randomness part comes, and in order to allow this randomness, you need this interaction phase. The prover commits to something, then the verifier gets to choose the random value, and then the prover continues, and it shows the evaluation of the polynomials.
Cool, thanks. I think that's nice, like this interaction where you essentially need to commit to whatever you already, like the list that you already want to prove the permutation argument on. I think that was an interesting part of the design. Cool, thanks. So yeah, let's do some, I guess, questions.
Okay, let's read some questions. So Harish is asking, there was a Stark at home on recursive Starks that prompts this. I guess this is the question. Is there a story around outsourcing computation and approving to, say, AWS and have the on-chain verifier being able to accept that that computation was done correctly?
It's a valuable concept to have provable computation. For example, if you want to run machine learning algorithms on AWS, big machines, a lot of computation, we want to know that AWS computed correctly, they didn't fool you. You can create proofs for this. It will be a lot more expensive than just running the computation itself, so there is a big overhead. But if it's very important to you, you can do that. We haven't done everything like
this.
I
think that the main issue there is the overhead. It's going to be much more expensive, and I don't see a lot of cases where it's important enough to get the proof that you will actually want to pay.
Yeah.
Next question by Bobbin. Cairo introduces an extra interaction step during trace commitment. Are there any instances when more than one extra interaction step is needed, i.e. committing to trace in 3 or 4, etc. stages?
So the answer is yes.
Do you remember why we?
I don't remember them. I definitely So I remember one example.
No, read write, I think.
No, read write can be done with one interaction.
Maybe general built-in, something like that.
Yeah, so allowing users to write their own built-ins and then combine them into a proof. So this requires, I think, 3 steps of interactions. Yeah. So 2 in addition to, and I think that there was another example which requires additional 1, but I don't remember what it was. So, but the answer is we had some cases like this.
But it costs in a way.
Yeah, it adds more. It adds to the verification time and to the proof length. Mm-hmm. Every interaction step it costs.
Yeah. I guess it raises, I don't know to answer this question now, but it raises this interesting complexity question, which is what addition do you get with more interaction? Which is very interesting.
Linear.
What?
No, as a complexity class. Problems that you can solve with. Yeah.
Higher depth or something like that.
Yeah.
Okay. So next question by Han. Does the Cairo virtual machine have a fixed amount of different segments, program, execution, user, built-in segments, or it can be dynamic and adjusted on demand?
Dynamic. That was an easy one.
Okay. Extending Kobe's question, how does it differ in general from TinyRAM constructions in SNARKs, where it is also like an opcode-based approach? So this is by Kevondre.
Yeah. Okay, so I want to answer. So, okay, let's start. There are 2 versions of TinyRAM. There is TinyRAM and there is von Neumann TinyRAM. So I'll answer on both of them. So I'll start with TinyRAM. TinyRAM is not a von Neumann machine. Basically, you take a TinyRAM program and you compile it to a list of polynomials, and then you get a list of polynomials that corresponds to your program. So it's easier to program this way. It's more easy to program this way compared to actually writing the.
Yeah, I would like CAD software to design an FPGA or some circuit.
Yeah. Okay, so this is and I think this is a huge difference. So now I'll answer about von Neumann TinyRAM, which is much more similar to what we are doing in Cairo. So von Neumann TinyRAM is also a von Neumann machine, Turing complete, and everything. And the main issue there is that it's not really optimized for performance. It just gives you the Turing completeness, but most of the opcodes deal with, and Michael, correct me if I'm wrong, but so the opcodes deal with integers modulo a power of 2, similar to the way x86 does, and if you compare
I
it
don't
to...
remember exactly.
Yeah, okay. So this is what I remember. I apologize if I'm mistaken.
Okay.
And Cairo, for example, in Cairo, we decided that we want things to be very efficient. So you deal with field elements. Now it costs when you want to write a program. You need to understand what you are doing, and you need to understand that if you divide 3 by 2, you don't get the integer value of the division, which is 1. You get some high number, which is 3 divided by 2 in the field. So it has a lot of disadvantages, but we thought that we want to give the programmer the most efficient way to program. I think this is the main difference between Cairo and the von Neumann TinyRAM is one is efficiency, and the second thing is the Cairo runs on stacks, which handles the universality of the constraints in a better way than snarks. But this has to do with with the level beneath Cairo.
Yeah, just say from a machine architecture point of view, TinyRAM had more instructions, and those instructions looked a little bit more like a standard computational CPU, and Cairo has fewer of these instructions, and they're more algebraic and field friendly.
Yeah, other examples are the ones that we discussed earlier. So in TinyRAM you have read-write memory, and you don't have built-ins. So moving to a read-only memory and adding built-ins, again, it's all about efficiency.
Yeah. Cairo has about 50 cells per instruction. Who else can say that?
Yeah, so I think in TinyRAM, in von Neumann TinyRAM, it's about 1,000 or so, something like this.
Yeah. Mm-hmm. The start version had like 130 or something, but also of high degree. Okay, so I suggest maybe Alexei and Kobi, we do one more round of your questions, and then we take one final round of questions. There are a few more that we haven't answered yet. Let's so interleave. So Alexei, please, and then Kobi, and we'll take the last round of questions.
Okay, so I just in order to, because it's the last one, I'm going to convert one of my question to the quick comment. There was a question asked about AWS and the outsourced computation, and one interesting actually example of this is to outsource the computation on a large database that is stored somewhere else where you cannot store, and essentially you're querying the database, and each query returns with the proof that it is in fact correct, and so it's kind of very similar to blockchains. But my question is, the one that I selected is that, can you share some of the characteristics of your, obviously behind the Cairo language, there's this provers that you currently have, and I'm assuming that you have some sort of state-of-the-art provers. And can you sort of give us the idea how much can they prove? For example, if I have a Cairo program which ends up having, let's say, billions memory cells, or trillion memory cells, or million, like how much can it prove in a reasonable time? And also, can these provers somehow get this computation distributed? So what can we hope for? Like if I have a program with 1 trillion cells, is it going to work?
Okay, so let's start with, so currently on a single machine, in a reasonable amount of time, you can do millions of Cairo steps.
What do you mean by single machine?
On
single CPU?
No, not on a single CPU. On an Amazon machine with a lot of CPUs, but one machine, not distributed. I mean, so you can do millions of steps. So you need to multiply it by 50 if you want to get the number of tracers.
It's million Cairo steps, you mean?
Yeah, millions of millions of Cairo steps. On larger machines, you can do more than that, and this grows linearly with the machine. So it depends how much you're willing to pay for the machine. And regarding future steps, then for example, you can do distributed proving. and use a lot of machines, and you can use recursion in order to do distribution, recursive proofs. This is another direction that we are looking into.
So the biggest constraint is number of Cairo instructions, right? It's roughly the
yes,
millions.
but and more specifically, the memory consumption of the traces.
Well, it depends on the program. If a program uses a lot of hashes, and it's the hash built-in.
Yeah, right. Yeah. So it depends on what the program does.
Okay, but it's in millions, not in billions or trillions at the moment, right?
Right. But I think it depends. If you are counting steps, then yes, it's in the millions. Yeah.
Okay, thank you.
So
yeah, right. So I guess let's go with something that's a bit easier. So you described like kind of how built-in works, and you touched maybe a bit on that, but what built-ins you have today, and how come when you implemented something like Ketchup very recently, you didn't need to add a built-in?
Yeah. Okay. So I'll start with the easy question of what built-ins we have today. We have a built-in for the Peterson hash. We have a built-in for rain check, which allows you to check that to compare numbers and things that are very natural to do when you program. And we have a built-in for ECDSA. The signature
for technical reasons.
Yeah, it's not really a built-in. And the recent built-in that was added in the last month or so is the bitwise operation built-in, which allows you to do AND or XOR on numbers, and you can. And we're currently actually working on a built-in for Ketchup and other built-ins that will make certain tasks much more efficient. But it turned out that even if you want to program Ketchup in Cairo using only this bitwise built-in, it's not that bad. It's less efficient than the built-in, and the built-in will still help. But apparently, using the bitwise built-in gives a good result.
So you would say that maybe, like, when people write snarks or like R1CS stuff, they're very worried about implementing things like SHA-256 and things like that. You would maybe suggest them not to avoid doing that in Cairo with the existing built-ins?
Not to avoid?
Like, not to avoid implementing these functions that they are scared of doing in snarks.
So it requires, you need to be really efficient when you're doing it, because then every instruction counts, and every trick that you can do, you should.
So we still have tricks to do it efficient.
Yeah, if you try to write Ketchup in a naive way, it will be much more expensive. So I'll give one example, which is easy to give. You can XOR. The values that you can store are 251 bits, and if you look at the algorithm for Ketchup, you need to XOR values of 64 bits. So if you just implement as is, you use only one quarter of what you can do with the built-in, and you would lose about a factor of 3 in the efficiency. If you do multiple Ketchups using the same, so you do 3 Ketchups using the 251 bits, then you get a much better result. And this is one example.
Okay. Thanks.
So let's briefly take the last 3 questions. And first one, on Hans' question, if you change the built-ins / number of columns, does this change the verification procedure?
Yes.
Yes, it does, but not in it's automatic. So we have code generation for this part of the Solidity contract.
Just with respect to single verifier to check everything, then
Yes.
okay, first of all, today we have a few layouts in the verifier, like 4. Each one has slightly different constraints, but on our roadmap is having a dynamic verifier that can verify everything.
Yeah, but if you add new built-in, then you definitely you have to change the equations.
Okay, next question by Lou. Hello, would you be able to reiterate or expound on what functionality within Cairo allows the checking of a greater than expression of 2 elements within a finite field, or a less than, just not an equality assertion?
Yeah, so this is not directly part of Cairo. It's a built-in that does exactly this.
Yeah, it checks if a field element is less than 2 to the 128, and use it to compare things.
Yeah, it's also explained in the paper.
Yeah.
Okay, the mathematician in me just wants to point out that actually as field elements in a finite field, there is no ordering. But I guess what you mean is, if you take the representation of the field element and view it as the integer, and then you want to do that. Okay, so there's a bit of
the nitpicker in you.
No, it's okay. Last question by Bobbin. How many trace columns do programs written in Cairo use, including columns used for memory, built-ins, etc.?
Wow, it's automatic. I don't know.
What? No, how many trace
columns?
Trace columns? Around 20, 25, I think. It's a question of you need to. So the number that's more interesting is the trace cells. The product of the number of rows by the number of columns, and we play with it. So that we'll have around 10 to 20 columns, because we found that this gives the more efficient proving.
Yeah, I just want to mention the concept of virtual columns or subcolumns. We don't need actually another column for the memory, something like this. Sometimes the columns we need are like half the size or quarter the size, and we can embed them all together. So we just have a lot of virtual columns of different sizes, and we just pack them as efficiently as we can in as few columns as possible.
Yeah, this is also mentioned in the paper, so you can read about it there if you want.
Yeah.
Okay, we're pretty much almost done. So any parting words by Alexei and Kobi?
Alexei, you're muted.
No,
sorry, now I'm muted, sorry.
Okay.
Yeah, just to say that when I read the, although I would slightly disagree with Mikhail, what he said in the beginning, because he said that if you're just programming in Cairo, you don't really need to read the paper. But actually, I would say that you probably still should, because it gives you quite a good idea. I mean, at least to me, it gives you a bit more confidence about you're actually understanding what you're doing. Like, what are the efficiency? I mean, of course, it doesn't give you the whole picture about what is the efficiency limitations, but it gives you much better understanding why there are built-ins, why they didn't not. I mean, that was one of my questions, but we didn't get to it. But the paper explains it. Why certain things like hashing were not implemented as opcodes, what kind of implication it has, and why they were done as built-ins. So yeah, this actually, I recommend people reading at least as many chapters as they can, because it gets harder. Even if you read the first 3 chapters, it's still a good result. Yeah, that's it for me.
So maybe I'll do the same here, and I'll disagree with you, Alexei. I think the experience that I had when I started dealing with Cairo and StarkNet and stuff like that is that I dove right into the code, and I found that a really pleasant experience. Like seeing the examples and seeing the documentation, you can do pretty complex stuff and express non-trivial business logic really nicely. So I would recommend people to do that. I think that's a really nice and pleasant experience. But definitely things become much more clear when you see some strange things about temporary variables and like the whole difference between FP and AP and all that becomes much more clear when you then read the design of why the program works now after I did all this magic. But you can do this magic even before reading the paper.
Yeah, I just want to say about the temporal thing because it's one of my pain points of mine. I really hope we can put in maybe not the 2.4 feature and the features like a var feature, so you just declare vars and you don't need to worry about revoke things and locals temporals.
Yeah, it's not part of the. It's not something that was part of the Cairo instruction set. It's just it can be implemented in the higher level language.
Yeah.
This feature, but it turns out to be more complicated than we thought.
Yeah.
Okay, so thank you all for joining us on this Stark at Home. Thank you, Michael, Shachar, Lior. Thanks, Alexei and Kobe, and thanks to the audience for terrific questions. Next step, you should read the white paper and, or even better, start building with Cairo and just try it out. See you next time. Bye.
Bye.
Bye.